Okay, we are at lesson 19, comparing actual areas from scale drawings. So the additional materials you'll need for this is a ruler with inch markings on it. And we're going to start by answering questions or examples 1 through 3. You're going to identify the scale factor, find the areas of the two figures, and calculate the ratio of the areas. As we complete a few more examples, we can be guided to the understanding that the ratio of areas is the square of the scale factor. So let's take a look at example 1. So, based on comparing the sides, so let's say we compare 4 units to 8 units. Well, if this is the actual, notice that it is smaller than the scale drawing, which means this is a magnification and our scale factor is going to be greater than 1. So that lets us know that we would set this up comparing 8 units to 4 units, which when we reduce this, it's a scale factor of 2 or 2 over 1. We could either even do the other units. 6 units to 3 units is still a scale factor of 2 to 1 or 2 over 1, which again is just the whole number 2. So when we look at the area of the actual picture is 12, because 4 times 3 is 12, or you can count up all the little boxes and you'll see that it's 12 square units. Remember that the label is important. This is square units, not just units. So now the scale drawing area, if we were to count all this up, or just multiply the two sides, 6 times 8 is 48. This would be 48 square units. So what is the ratio of the scale drawing area to the actual area? Well, it would be 48 over 12, which is right here, and 48 over 12 reduces to the whole number 4. Well, what do you notice about the scale factor 2 and the ratio of the scale drawing is 4? Let's take a look at the next example. All right, so for example 2, our actual picture is bigger than our scale drawing, which means this is a reduction. And our scale factor is going to be less than 1. So if we were to compare these two, the scale drawing to the actual picture, it would be 2 units over 6 units, which reduces to 1/3. Or if you took the other sides, the corresponding sides, it would be 3 units to 9 units, which is again 1/3. So the scale factor is 1 unit to 3 units. The actual area would be 9 times 6, or again, if you want to count all these up, you'd get 54 square units. And the scale drawing area, 3 times 2, is 6 units, or 6 square units. Well, if we're going to compare the scale drawing to the actual drawing, that would be 6 over 54, which reduces to 1 over 9, or 1 to 9, or 1/9. All right, so what is the relationship between 1/3 and 1/9? All right, last example. We have our actual and we have our scale drawing. Again, the scale drawing is bigger than the actual picture. So that means we are comparing 8 units to 6 units, or 12 units to 9 units, which reduces to 4 to 3, 4 over 3. So now figuring out the actual area, you're probably wondering, well, how is this 27 if 9 times 6 is 54? Well, remember, this is a triangle, and once you multiply the sides, 9 times 6, you need to take half of that. So 54 divided by 2 is 27. The same thing with our scale drawing. 12 times 8 is 96, and half of 96 is 48. So again, the ratio of the scale drawing area to the actual area would be 48 over 27, which reduces to 16 over 9. And again, compare these two numbers. What is the relationship between 4/3 and 16/9? All right, so let's look at completing the result statement on the lesson worksheet. When the scale factor of the sides was 2, then the ratio of the area was 4. When the scale factor of the sides was 1/3, the ratio of the area was 1/9. And when the scale factor of the sides was 4:3, or 4/3, then the ratio of the area was 16/9. So based on these observations, what conclusion can you draw about the scale factor and the area? Well, the ratio of the area is the scale factor multiplied by itself, or squared. So 2 squared is 4, 1/3 squared is 1/9, and 4/3 squared is 16/9. So if the scale factor is r, then the ratio of the area is r squared to 1. Alright, so why do you think this is? Why do you think it is squared as opposed to cubed or something else? Or maybe even multiplied by 2? Well, when you are comparing areas, you are dealing with 2 dimensions instead of 1 dimension. So that is why we square it. So how might you use this information in working with scale drawings? Well, in working with scale drawings, you could take the scale factor r and calculate r squared to determine the relationship between the area of the scale drawing and the actual picture. So given a blueprint for a room, the scale drawing dimensions could be used to find the scale drawing area and then applied to this new relationship to determine the actual area. The actual dimensions would not be needed. So as long as you knew the area on the scale drawing, you wouldn't need to know what the length and width of a room is in order to find the actual area. Alright, so suppose a rectangle has this area of 12 square meters. If it is enlarged by a scale factor of 3, what area would you predict the enlarged rectangle to have based on examples 1 through 3? Look and think carefully before you continue. Alright, so let's see if you came up with this answer. If the scale factor is 3, then the ratio of the scale drawing area to the actual area is going to be 3 squared to 1 squared, or 9 to 1. So if its area is 12 square meters before it is enlarged to scale, then the enlarged rectangle would have an area of 12 times 9. So resulting in the area of 108 square meters. So if the area is 12 meters and it's enlarged by a scale factor of 3, then it's going to end up being 108 square meters. Alright, let's take a look at example 4. You are going to solve this example by yourself. There's at least 3 different ways to come up with the correct answer, which I'll give you. It's 750 square meters. So when you are finished, continue the video to see which method you chose. So go ahead and pause the video. I already gave you the answer. Just go ahead and come up with the process. How do we get 750 square feet? Alright, so you should have finished example 4. Let's take a look at a couple of methods and see which one yours matches up with. So, example 4, based on our basketball problem from before, method 1 could be to use the measurements we found in the lesson to calculate the area of the half court. Well, if it was 25 feet by 30 feet, then 25 times 30 is 750 square feet. So that's one way you could do it. Here is method 2, using the scale or using the scale factor. So this can be applied to the given scale with no unit conversions shown on the left, or you can use a scale factor shown on the right. So both options are included here because you could have possibly done this, and why one method works, or actually both methods work, and which one would you prefer. So using the scale, if the ratio of the area is 1/15, then we square that, then our area scale is 1 to 225. So if our scale area drawing is 2 inches times 1 2/3 inches, that gives us 10 square inches. And if we know that our scale factor, or our scale, is 1 to 225, and it is equal to an area of 10 square inches, then by multiplying by the reciprocal 225 times 10 we actually get 750 square feet. If you're looking at the scale factor, it'd be 1 to 180 inches squared, which is a pretty big number, the scale factor being 1 to 32,400 inches. So the scale area drawing is 2 inches by 1 2/3, which gives us 10 square inches. And now we have to multiply 10/3 by 32,400. So the actual area is 324,000 divided by 3, which when you convert it into feet is 750 square feet. So you can see that there's several ways to get 750 square feet, but I'm sure you can see which is the easiest way to do that. And what method would you prefer? Is there a time when you would choose one method over another? Well, if we already don't know the actual dimensions, it might be faster to use method 1, the ratio of the areas. If we are recarpeting a room based on a scale drawing, we could just take the dimensions from the scale drawing, calculate the area, and then apply the ratio of the areas to find the actual amount of carpet we need. So complete your follow-up question in your lesson worksheet. Does the actual area you found reflect the results we found from examples 1 through 3? And explain how you know. Well, yes, the scale of 1 inch to 15 feet has a scale factor of 1 to 180. So the ratio of the areas would be 1 over 180 squared, or 1 to 32,400. So if the drawing area is 2 times 1 2/3 inches, or 10 square inches, and the actual area is 25 feet by 30 feet, or 750 square feet, or if we convert that to inches, 108,000 square inches, then we take the ratio 10/3 over 108,000, which converts to 10 over 324,000, or 1 to 32,400. So you can see the relationship between the actual area and the scale factor. So although it would be more efficient to apply this understanding to scale and eliminate the need to convert units. So if we use a scale of 1 to 15, or 1/15, then the ratio of the area is 1 to 225, and the drawing area is 2 times 1 2/3, or 10 square inches. Well, the actual area is 25 feet by 30 feet, or 750 square feet. And the ratio of the area is 10/3 to 750 square feet, or 10 to 2,250, because again, 10/3 times the reciprocal of 750, which is 1 over 750, gives us 10 to 2,250, and we can reduce that down to 1 225th. Notice that this corresponds with the ratio when we square this. 1/15 squared is 1 over 225. So here's a challenge question. What do you think the relationship is when considering 3 dimensions? For example, if the scale factor comparing length of a pair of cubes is 1 to 3, or 1/3, what do you think the ratio of the volumes is for the same cubes? We're not going to answer this now, but think about it. What do you think would happen? Alright, so let's take a look at exercise 1. Complete exercise 1 and then continue the video to compare your results to the answer. So go ahead and pause the video and do exercise 1. Alright, so let's see what you have. Well, the triangle depicted by the drawing has an actual area of 36 square units. Now that is not what is shown here. They're giving this information. So the actual triangle is 36 square units, and this is a scale drawing. The scale of this drawing, note each square on the grid has 1 unit. So the scale drawing area is 1/2 times the length times the height. So 3 times 6 divided by, or times 1/2 is 9 square units. So this is 9 square units, and now the ratio of the scale drawing area to the actual area, would be 9 over 36. Remember, the 36 comes from the information we were given. Well, that's going to equal our ratio or rate squared. So what two numbers multiplied by themselves would give us 9/36? Well, that means our scale factor would be 3/6 because 3/6 times 3/6 is 9/36. Well, 3/6 can be reduced to 1/2, so therefore the scale is 1 unit of the length represents 2 units of the actual length. So if this is 3, then the actual length would be 6. And if this is 6, then the actual length would be 12, which would make sense because we would have 6 times 12 is 72, divided in half would be 36. Right, exercise 2. Use your ruler to measure. You want to measure the dimensions of the apartments. You need to measure the dimensions of the closets and the dimensions of the bathrooms. So go ahead and do that and then continue the video. Remember, you're doing this in inches. So this is what you should have. 2.5 inches for the suburban apartment times 2 inches. And if for some reason when you measured this it didn't come out completely correct, go ahead and just edit your work to show these dimensions because this is what we're going to be working on. The closet is 1.5 inches by 1/4. This closet is 1 inch by 1/4. The bathroom is 1/2 inch by 1, and the kitchen is 1/2 inch by 1. Over here we have a 1/2 inch by 3/4 of an inch, 1/4 times 1/2. The other closet 1/4 times 3/4, and over here we have 3/4 times 5/8. Alright, so using the dimensions, complete part A. Go ahead and continue the video when you are done. Alright, so for part A, you should have this. As far as the scale drawing area, 2.5 times 2 is 5 square inches, and 2 times 1.5 is 3 square inches. So what would that be in actual area? Well, if 5 taking the 12 squared is 144, so 5 times 144 is 720 square feet. Using the scale factor for the city apartment, it would be 16 squared. So 3 times 256 is 768 square feet. All right, go ahead and complete part B and continue the video. All right, for part B, you were asked which apartment has a closet floor with the more square footage. Well, now you've got 2 closets, so that's why you have to add 1 times 1/4 plus 1/2 times 1/4. Add those together, and the total closet area is 5/8 square inches. Same thing with the city, 1/4 times 3/4 and 1/2 times 1/4. Add those two together, and you have 5/16 square inches. And then to figure out the actual area, again using the same thing we did from the apartments up here, since we already know it's 144 inches, it's 5/8 times 144 is 90 square feet, and 5/16 times 256 is 80 square feet. So the suburban apartment has greater square footage in closet floors. All right, now do the same thing for part C. Okay, for part C, you were asked to figure out who's got the largest bathroom area. So since there's one bathroom, the area 1 times 1/2 is 1/2 square inches. 3/4 times 1/2 is 3/8 square inches. And then applying the ratio again, the rate, 144, means that this is 72 square feet. And 3/8 times 256 is 96 square feet. So the city apartment has the largest bathroom. All right, now complete part D. All right, so for part D, if you have a 1-year lease for a suburban apartment that costs $750 per month and a 1-year lease for the city apartment is $925, which offer or which apartment offers the greatest value in cost per square foot. So here is your rate, money per square foot. So that is your key to how you're setting up your ratio. It's going to be dollars over square feet. So figuring that out, it'd be $750 over 720 square feet is $1.04 per square foot. And if you do the same thing to the apartment or the city apartment, 925 over 768 is $1.20 per square foot. Therefore, the suburban apartment offers a greater value. That means it's cheaper, $1.04 versus $1.20. All right, so to wrap up, when does giving a scale drawing, how do we go about finding the area of the actual object? Well, there's a couple of methods. First method, compute each actual length based upon a scale, and then use that actual dimensions to compute the actual area. Or you can compute the area based upon the given scale dimensions and then use the square of the scale to find the actual area. So describe a situation where you might need to know the area of an object given a scale drawing or a scale model. Well, let's say something where you might need to purchase materials that are priced per area, something that has a limited amount of space to fill or take up when comparing two different plans. All right, we'll talk to you in class.